this class, we are going to finish optimization. The questions kind of fall into, the ones that are left anyway, fall into a variety of categories. There are going to be some questions involving rectangular fields. There's a whole bunch of questions involving various shaped boxes, 3D shapes, mostly called cuboids, but they call them boxes, and that's fine. And there's a weird poster question. There's a crossing a river question, and then we finish with oil refinery questions. And a little note here, for some of these questions, the optimization function, when you differentiate it, right, the f dash of x guy, and you're trying to find out when it's 0, it might not be possible to algebraically solve them because they are so ugly that you can't really solve every equation, right? Now, when that happens, do you know, you just stick it into Desmos and find out where it crosses the x-axis. So an example is, suppose you had your derivative and it was this guy. You don't really want to try and solve that. Would you agree that would not work well, right, algebraically? So imagine you plug it into Desmos and you just find out there, right? Wherever it crosses the x-axis is the number you look for. So that is going to kind of happen. Just giving you a heads up. So when it does, we won't be too surprised. So let's jump right into our first question. And we're going to do a rectangular field one. It's going to be 9 or 10. Let's find out which one. I'm going to do 10. A farmer wants to fence an area of 37.5 million square feet. God, this must be Texas. And his rectangular field looks like this. And he splits it like that. And we are told that the area of this rectangular field is 37.5 million, million square feet. And we are being asked to find the minimum amount of fence. So that's going to be our quest, to find the minimum amount of fencing. So I go to a question like this and I start putting names on things. I'm going to call this distance here X. I'm going to call this distance here Y. And the total amount of fencing that you would need to build this guy, including the bit in the middle, would be 2x plus 3y. Are you comfortable with where the 2x plus the 3y are coming from? Now, don't I need to find that y in terms of x? Right, that's my next goal. Right, find out what y is in terms of x. And you always use this fella up here, right? You're told the area thing. So if I tell you the area of this rectangle, then it's xy. If I tell you the area is 37.5, then that's what xy is. And that means that y is going to be 37.5 over x. You see how that piece of information got me the y in terms of x's. So the optimization is now 2x plus 3 lots of this guy. And that's going to be 2x plus 3 times 37.5. 3 times 37.5, and that's 112.5 over x. We have just finished step 1. Find the optimization function. Great. Now, that's the hard part. To me, once you've got that, the rest is kind of standard. Aren't I going to differentiate this guy and find critical numbers? And one of those critical numbers is going to be the one I want, right? So I'll differentiate it with respect to x, and that gets me 2. And can you just trust me on this one? You can check it later. But that's what you get when you differentiate that guy. And I've now done step 2. Now, isn't step 3 find the critical numbers? And one of those critical numbers is the solution, right? Now, there are two kinds of critical numbers. Let's go for the equals 0 one first. Then 112.5 over x squared would have to equal 2. Are you happy with that? There's different ways to solve this question. That makes sense? A little cross multiply. A little divide by 2. What's that going to get me? 56.5. Plus or minus the square of 56.5. Plus or minus 7.5. Unfortunately, it's 7.5 million feet. But, you know, that's fine. There are, in fact, in this question, 3 critical numbers. There's a positive 7.5 million. There is a negative 7.5 million. And isn't there an undefined critical number at 0? Let's see what we can do about that. Why am I going to ignore that one? That can't be the answer. Why can't negative 7.5 be used?
Can't have negative fencing.
Yeah, that makes sense. Would you agree having no fencing is probably just as bad? Only one guy, that's our solution. Now, what does that transfer to? Well, when you look at the question, it doesn't ask you, tell me what x is, which really should be written down the long way, right? 7,500,000. It asks us for the short and the long dimensions of the rectangle. Remember the guy up here? Now, we've just found out that that guy is 7,500,000. So that's going to be one of the two boxes, because they have a box for the small one and a box for the big one, right? So we know the big one is going to be that number, right? Won't this be the other guy, right? Long, short. Want the dimensions essentially. Now, to find this guy, won't you have to go over here, right, and divide by 7.5, and you get 5. So the final solution to this question is that if you want to have a field with 37.5 million square feet and you want to split it into 2 like this, then you'll have to do a 7.5 million by 5 million. I guess I should put all the zeros in. That's the dimensions you're going to have to make it. Are we good with that question now? Now, a lot of the questions that are going to happen from now on, I am only going to get to this step, right? The optimization function with x's. The differentiate me, find the critical numbers, you're going to basically, you fill that in yourself later. Well, the next group of questions are all to do with boxes. Question 11 has a box which has a volume of 62,500 cubic centimeters. And this box is square and it's open top. And we are being asked in this question to find the dimensions of this box that minimizes the material used. Okay, let's start labeling things. Since it's square, it's x by x. And in this case, distance, I'm going to call it y. What do you think they mean by minimizing the material used? What am I calculating when I'm finding material used?
Surface area.
Agreed. Now in this shape, since it's open topped, let's call the optimization function S for surface area. The base of this shape has an area of x squared. Would you agree that this box has 4 side panels? Right? And they're all the same area, right? What's the area of any one of those 4 side panels? Like this one here. What would its area be?
X times what?
Okay. And since there are 4 of them, it's 4xy. Great. Now, they've told me this piece of information. Isn't this the guy that's going to allow me to turn this y into x's? So let's do that at the side. The volume of this box is its length times its width times its height. That's x squared y. Its volume is 62,500. That makes y 62,500 over x squared. Are you happy about how I worked with that piece of information to get the y guy? That makes surface area an x squared plus 4x times this guy.
For the surface area, wouldn't it be 2x squared? Because there's the bottom as well.
Ah, but this is open topped. So the
Oh, okay.
top
I didn't
isn't
catch
there.
that.
Yeah, if it did say it had a top, you're right, that would have been 2x squared. No. We have an x squared. That's 50,000 over x. There you go. Step 1. Here is your optimization function. Right, can you imagine differentiating that, finding its critical numbers, and one of those critical numbers is the guy you want? Are we good? Right, differentiate, set it to 0, critical numbers. Let's look at a more complicated version of that. And you think, well, what could be more complicated? How about question 13? Looks very similar. Square base box. Right. X by X. Y. Like that. It even has a volume. You're told that its volume is 10 cubic meters. I know with that. It's nice. Like that. And we're being asked to minimize its cost. And you think, well, what do you mean the cost? Well, here is some more information. The material that is used on the base costs $20 a square meter. And the ones that make up the side panels, they only cost $10 per square meter. So I guess, can you imagine it's a box where the bottom is more reinforced than the sides, you know, for whatever reason. You're made out of wood or something, right?
Is this an open top?
And it's open topped again, yes.
Okay.
Now, let's do this fella first. Since the volume is x times y, and that's x squared y, and that's 10, just like we did in the other question, don't we now know what y is? The optimization function is going to be called C for cost. Okay. The base has an area of x squared, agreed? But it costs $20 a square meter. So $20 times x squared. Does that make sense? For that's how much that would cost. Right, his area is x squared, $20 a square meter, 20x squared. Now, there are 4 side panels. But don't each of them cost $10 a square meter? You see that I've had to adjust the formula to include the cost, not just the area. So it isn't x squared plus 4xy now. It's the cost times x squared plus the cost times 4xy. And that becomes 20x squared plus 40xy. And then that y gets replaced by this guy. So it now becomes 20x squared plus 40x over 10 over x squared. And our optimization function is now that guy. Now, if you can find that guy, can't you differentiate him, find out where he's 0 and get the critical numbers? And one of those critical numbers is the guy you're looking for. You see they're getting sneakier and sneakier, right? Started off with a box with no lid. Now it starts off with a box with no lid, but the side panels cost different from the bottom panels. Can you imagine they could just keep adding more and more things to make it a little bit trickier? But eventually you've got a cost function. And that's what you're after. This is the guy you're trying to minimize in this case. Are we good so far? Any questions before I move on? Okay, next one is poster question. So they do have a picture with this one. They didn't have a picture with any of the other ones. This is a poster. And inside this poster, they have a picture. And we don't know what the picture dimensions are, so I'm going to call them X and Y. This poster, with a picture in the center, has, I know it doesn't look the same, but pretend I drew it better. 12 inches that way, inches or centimeters? Oh, centimeters. And 8 centimeters this way. And we're told one more thing. The area of this picture is 1,536 square centimeters. And we have to find, so this is what we have to optimize. Poster, right, the whole thing, with the smallest area. Okay. Let's take this piece of information first. The area of this picture is X times Y. If you tell me the area is 1536, then that's what XY is. So 15 over 36x, that's what y is. So I now know how to turn y into x's. Just getting that out of the way. Now let's look at find the poster area. So I'm going to call it P for poster. Well, if I want to find the area of the poster, don't I need to know this dimension multiplied by this one, right? Okay. Now you got to think a little bit about this. If that distance there is x, What's the distance from here to here? That middle bit is x. What's the total distance from one side to the other?
X plus 16.
Great. Now, if this distance here is called y, what's the total distance top to bottom going to be?
Y plus 24.
You all happy about where those numbers are coming from? Now, won't the area of this poster then be x add 16 multiplied by y add 24? And I now know what y is. It's a really ugly, that guy, plus 24. And we have finished step 1. Would you agree? It's not the prettiest formula in the world, but isn't it a function of x? How could you differentiate this? What would you do?
You could use the product rule.
You could. And nothing wrong with the product rule. It's correct. It'll work. I just don't want to. So how could I avoid using the product rule for something as ugly as this? Because it is ugly no matter what you do.
Foil.
Yeah. I'd probably foil it out and then differentiate it. At least it's power rules, right? Less chance of screwing up. It's probably going to be so ugly that you might have to put the derivative into Desmos to see where it crosses the x-axis, right? Because you're going to make it equal 0 and it's not. I'm guesstimating, I haven't done it, but I'm guesstimating it's probably so ugly you don't want to do it algebraically. And you got your answer. Are we cool with the poster? Any questions about that? Are you comfortable where the bits came from?
I think I'm good.
Okay, good is good. We are going to do the river one now. And this is going to be question 16. The river one has a picture. And the river one and the next question after it, the oil refinery, although they're totally different stories, do share quite a lot in common. So that's something. So here is the picture that they gave us. There is a river. And there's a guy at position A. And this river is 4 kilometers wide. And he wants to go to a position called B. And I'm trying to read down where it is. And the guy he wants to get to is here, position B. And the distance from there to here just also happens to be 4 kilometers, at least in my version is. And you're told some other things. There's a lot going on in this story. When he's in the boat, right? So when he's in the river, his speed, so the river speed is, what is 0? He rose at 6 kilometers an hour. When he is on land, his land speed is 8 kilometers per hour. Now, he has 3 situations, 3 ways to do this. Situation 1, he goes straight perpendicular to the side of the land to here, which is called C, and then from C to B. So he goes A to C, and then C to B. Oh, by the way, we're trying to minimize the time. So we're trying to find the quickest way for him to get from A to B. So that's the first way, right? For that, number 1. Number 2, Number 3. Okay, number 2. How else could you get from A to B? You're in the boat at A and you want to get to B. You could just sail right across to the other side and then walk 4 kilometers south, right? How else could you do it?
Go straight to B.
Okay, so you could just go A to B. And then there's a third kind of compromise. You could go to some point D and then from D to B. Could you imagine that there might be some sweet point where that would work, right? Where you don't row all the way because you're kind of slow at rowing, but you don't walk all the way and just row straight across because that's too far. There might be some kind of compromise in the middle. So what we have to do in this story is we're going to have to find what the times are for these 3 situations. And the first 2 are just number crunching. There isn't an equation at all. And the third one is where we have to do an optimization function. So I want to get situation 1 and 2 out of the way first. So here is situation 1 again. A to C is 4 kilometers. So let's find out what the time it would take. 4 kilometers traveling at 6 is 4 over 6. That's how long that would take. And from C to B is 4 kilometers at that speed. So that's 4 out of 8. And the answer you get is 1 1/6. So that's what, about 1 hour, 10 minutes. That's pretty fast. Let's look at situation 2 now. If you just rowed, right, all the way from there to there, A to B, right, you did that one. You need to find out what the distance from A to B is. Now, can you see a right angle triangle here? See it? Then won't A to B be the third side of a right angle triangle? So if I write down the square root of 32, isn't that 16 plus 16? And that's the distance. And I'm going to divide it by 6. And the answer for that version of the journey is 0.94 hours. Interesting. Now we have the last situation, which is the one that's going to cause us all the trouble, I think, because it is the optimization one. So there's an awful lot happening in that picture, so I'm just going to redo it again. Here's A, little dotted line, to here's C. There's the guy that I'm going to call D. And a little bit further on here is going to be B. So in the third situation, we're going to go from A to D, and then we're going to go, right, we're going to go that route, and then we're going to go that route, okay? Now, if I want to know the time it takes to go from A to D, don't I need to know the distance from A to D and divide it by the speed in the water, which is 6. Now, that distance from here to here, I'm going to call x. And that distance is fixed, so I'm going to call that 4. Do you see a little baby right angle triangle here? Then won't AD be the hypotenuse of a right angle triangle where the sides are 4 and x? And can I put x squared plus 16 in divided by 6? Are you happy about where the x squared plus 16 came from? It's this side squared plus that side squared, right? And then the square root of it. Why am I dividing by 6? That's the speed when you're in the water. So our time function is going to be the square root of x squared plus 16 over 6. Now, what about BD? Can you tell me the distance from B to D in terms of x?
That's just 4 minus x, isn't it?
Agreed. If this is x, can you see that as 4 minus x? And can I call that a half? Take away 1/8 x, right? So we have plus a half, take away 1/8 x. And there is your optimization function. Quite an ugly one, right? Can you imagine that when you differentiate it, it probably isn't very pretty? Then what you can do is put it into Desmos, find out where it crosses the x-axis and write down, I don't know, x is 1.234. Let's just pretend, I don't want to do the whole question because I don't have time. Let's pretend that that's what x is. Then don't you have to plug it into the original formula to find out what the time is? Now, what could happen? Well, one of two things could happen. Suppose it is that number, and I plug it in here, and I find that it takes 0.8 of an hour. Then won't that be the fastest route? But it could end up being 1.8 hours. In which case, if it is, won't this answer that we've already found, the direct route, be the quickest? And the reason why I'm saying that is that question 16 says you're going to get an unexpected solution, which makes me think that whatever this number is, it doesn't actually give you the best answer. Just rowing straight there does. Could happen. I guess you'll find out. Tell me tomorrow. Hey, I did all that hard work and I didn't need to. If you just rode straight there, it was quickest. That's what I'm guessing is going to happen. So we are now on our last question. Okay, oil refinery question. There is no picture in this question. So I'm just reading it out. And as I read it, I write pictures. Because you can't, if you notice, you can't really do these questions without a picture. You really need to visualize what the heck's going on. So an oil refinery is located on the north bank of a straight river. Okay, so I got a straight river. And here we have R. That's the oil refinery. And this river is 2 kilometers wide. Okay. A pipeline is to be constructed from the refinery to storage tanks located on the south bank, 8 kilometers east of the refinery. So can you imagine a little dotted line to here? Call that A. Over here, you have storage tanks. So that's the storage tanks. And the distance from here to here is 8 kilometers. And then it tells us that when you lay the pipe and you do it in the river, the cost is 800,000 per kilometer. And when you do the pipe on land, it's a lot cheaper. When you do it on land, it's only going to cost you 400,000 per kilometre. And we are being asked to find how to get from the refinery to the storage tank, right? How to do some pipes that do that. And we have to do the minimum cost. So that's the guy we're trying to calculate. Right. So far, so good. Now, just like the river crossing, there's actually 3 situations. Couldn't you just go from R to A and then from A to S? I mean, wouldn't that just be one solution, right? Pipe, pipe. Don't need calculus for that. Can we just calculate it? Now, from R to A is 2 kilometres, and it's going to cost you, because it's in the river, 800,000 a kilometre. Then you're going to add 8 more kilometres of pipe at 400,000 each. And that comes to 1.6 million plus 3.2 million, which gives me 4,800,000. So if you just want to go straight and straight, the bill will be 4,800,000. Okay. That's situation 1 done. Think of the river question. Tell me another way you could get from the refinery to the storage tank. We've done
Across.
Build it straight to it
straight
again.
across, right? Why don't we just go? Yeah, right. The green there. Now, if you just do R to S, right, then we know it's going to cost you 800,000, right, per kilometre thing. But don't I now need to know what that distance is? But if you look at it really carefully, isn't there a right angle triangle going on here? And this side is 8 and this side is 2. So according to Pythagoras, 8 squared is 64, 2 squared is 4, square root of 68. Are you happy about the square root of 68 and where that number's coming from? It's that distance. So on my calculator, the square root of 68 getting multiplied by 800,000. And this fella comes out to be 6,596,968 Now that I've found that, can't I cross that off the cheapest route? It's obviously 2 million dearer than that one, right? So it's not cheapest. And then we have the sneaky one. Wouldn't we just do a bit of each? Let's call this guy B. Couldn't I go from R to some point B? And then from B to S? And I am going to call this distance X. So I'm going to do as our third possibility. You build a pipe from R to B, and then you do the pipe from B to S. This is 2 kilometers. This is X. What is the distance from R to B going to be then? Two and X. What's the distance from R to B going to become?
Square root of 4 plus x squared.
Right? And because that is on the river, isn't that going to cost you 800,000 for every kilometre that's equal to? Right? When it was 2, you multiplied by 800. When it was whatever, that number, you multiplied. When it's that number. Now, almost done. What is the distance from B to S in terms of X?
8 minus x.
Great. Isn't that dead like the rowing story? And when you're on land, it costs you 400,000, so it's going to be 8 take away x times 400,000. And that's going to be the cost. The cost function is 800,000, the square root of x squared plus 4, because I just like it that way around, plus 3,200,000 take away 400,000x. Right, that guy, distribute these guys. So now I'm going to differentiate it. Okay, that guy I'm going to call x squared plus 4 to the half. I'm going to do a chain rule on it. And you're just going to have to trust me because we don't have enough time for me to show you in detail. But will you take my word for it? That's what you end up with. Okay. Now, that's easy. Big ugly number, but when you differentiate it, it's 0. That's pretty easy. You get that. Now, would you agree you probably don't want to solve that equals 0, right? Because that's step 2 done. To find critical numbers then, you need to find when this thing is 0. And so I am now going to go and do Desmos, I hope. Give me a second to find it. I thought I had Desmos, but evidently my mouse is being weird. Okay, I got it now. So let's solve that really ugly equation. So I'm just going to call it y equals. I guess I could call it derivative equals, but let me see why I want to. So I'm going to plug 800,000x divided by square root of x squared plus 4. Take away 400. Oh, wrong place. Take away 400,000. Now, that doesn't look like much of a graph, doesn't it? Almost look like it's a vertical line. But you got to remember that these numbers are huge. I don't need to see all the curves and the shape of the curve. Isn't the only thing I'm interested in is that guy, where it crosses the axis. And it crosses at a rather ugly number, 1.155. But we have found the only guy in town. Now, there might be, I'm not saying there is, but couldn't there maybe be another x at 42? Even if there is, won't I throw that away? Because in the context of this story, would you agree that'd be too far away, right? If I get a negative number, would you agree that would also be stupid? So I'm not even going to worry about it. So I'm really confident that's the only answer I need to worry about, right? The one that's in front of us. So now I'm going to return. And we have one last thing to do. Our cheapest journey, right now is 4.8 million. We're saying that if you land at 1.15 away from the sign, then walk the rest, is going to be cheaper. But to be sure, shouldn't I calculate the cost? all the other stuff. Now, why should I calculate that? Can you pretend that I calculated the cost and it ended up being 4,100,000? Then wouldn't that be the cheapest route? Right? But I could calculate the cost and it could be 4,900,000. Great. In which case, wouldn't that be the cheapest again? So in these later questions, because there were two other possible options, the optimal one, this one here, may not actually be the best. Actually, I know the answer. It is the best. But you need to check it. Because I strongly suspect that the previous question, the rowing boat question, I think if you row directly, it's going to be quicker. So you don't actually go somewhere along and somewhere down, right? The exit you get there won't be any good to you. I think you just row straight to the place. In the pipeline one, I know for sure that this number is going to be the best answer, but you should check it. And we did it. We actually finished, at least as much as I have time for, optimization. Was it as scary as I told you? Is it not as bad now that we've done it for 2 days? Okay, good luck. See you tomorrow.
Are you
Say
having
hi
office
and
hour?
say hi and bye-bye. What was that, Skylar?
Are you having office hour?
I am. I've been really hassled the last 2 days, but I'm just going to be there this time. I was doing other things, just couldn't get back to set up the officer quickly enough.
Okay. I'll be in there.
See you shortly.